I'm going to be talking about symmetry, forced rigidity. And the idea, or just to, let's look at an example. Oops. All right, so here's a graph. And it is symmetric with respect to the group that's generated by an order 4 rotation. And so what I mean by that, right, is if you rotate this 90 degrees, it will look the same. Now, it's a graph in the plane. If you just use, Lemann's theorem or Polchak-Geiger's theorem, you'll see just from counting edges and stuff that this is flexible. And the flex that you do to this, it just sort of comes from like shearing sort of this outer square. But you'll notice that if you were to do that, apply that flex, you would break the symmetry. So yeah, we're in the symmetry force setting. So this graph is flexible, but not symmetry force flexible. And last time, Tony talked about gain graphs and quotient graphs and how to represent a symmetric graph with a gain graph. And so just to sort of briefly review, we can express the above graph as a gain graph. And we'll let a squared, a cubed be the symmetry group. So one gain graph representation would be following. Where, so, and you all did this yesterday, so I'll be sort of brief and informal with this, but this vertex of the gain graph corresponds to this vertex orbit in the symmetric graph itself, and then the other vertex in the gain graph corresponds to the other vertex orbit. The two loop edges correspond to the fact that you have edges that stay within each of the orbits. And the label on them just corresponds to what element of the group you apply in order to get the other vertex of that. And this identity edge corresponds to the edges going between your vertex orbits. So yeah, I mean, does this all make sense? Are people comfortable more or less with going between gain graphs and symmetric graphs? If not, let me know. Okay. All right. So if people are okay with that, then I will continue. And again, I guess Tony also talked about using gain graphs to represent not just symmetric graphs, but symmetric frameworks. And so I'll just sort of take that for granted that you understand this. So the motivating question for this lecture is going to be the following. For a fixed rotation subgroup of planar Euclidean isometries, and I'll call this subgroup S, which S gain graphs are generically symmetry force rigid. All right, so is the question clear? All right, I will take silence as a yes.
So
yeah.
In the above one, where the question is the gain graph rigid? But
Yes.
we've shown that but you said above that the original graph is also symmetry force rigid. Oh, it's symmetry force flexible. Okay.
The above graph is symmetry forced rigid. It's flexible if you don't force symmetry, but it's symmetry forced rigid.
The gain graph or the original one? Or...
Both. Okay. So and this is sort of so and I guess this is what I mean. So corresponding to every gain graph, you have a bunch of infinitely many generic symmetric frameworks, and then the question is, are those generic symmetric frameworks symmetry force rigid?
Mm-hmm. Okay.
Does that make sense?
Yeah.
Okay. Okay. Cool. All right, and so I'm gonna take sort of an algebraic perspective on this, and this is going to be the same kind of perspective I took in the last lecture I gave in this course. And so let's recall. Sorry. Before I get there, I'm getting a little ahead of myself. So yeah, just some notation. I'll use C to the E, R to the E to denote vector spaces whose coordinates are indexed by E, where E is a set. Usually the edge set of a graph or the arc set of a gain graph. And then if F from, say, I guess any field, K to the, say, D to K to the E is a polynomial map, I'm going to let J of F is the matrix whose rows are given by differentiating TIATING the component functions of F, right? So, you've seen this 100 times in this rigidity context, where usually F is just going to be the polynomial given by a bunch of pairwise distances between endpoints and d dimensions. And then the Jacobian of that is this rigidity matrix. And then so more specifically, sorry. One last definition, and I'll say M of F is the matroid of linear independence of the rows of J of F. All right, and so for example, if Dij is just equal to, say, xi minus xj squared, where each xi is just a vector of indeterminants, then as we let ij range from 1 to n, then this is a polynomial map. From, say, r to the dn to r to the n choose 2. And m of this map is the rigidity matroid, the d-dimensional rigidity matroid. Okay. All right, and then just to, I know this is probably all review, but just since I'm going to sort of kind of generalize this picture a bit, I just want to be a little pedantic about this. Okay, so I'll let d g be the polynomial map from r to the we're gonna eventually stick to the plane, so I might as well just do that now. Yeah, I'm just gonna let d to the g be this map. That sends a point x1 dot dot xn y1 dot 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 yn to the vector xi minus xj squared plus yi minus yj squared over all edges ij of g. Okay, and we know that G is rigid if and only if the rank of the Jacobian of D to the G is equal to the rank of the Jacobian of D to the complete graph. Okay. And then in other words, G, or the edge set of G, is a spanning set in the matroid of this map for the complete graph. Okay, so hopefully all this is review. And now I just want to adapt this to the symmetry force setting so that we get some good sort of concrete language and tools for talking about rigidity in the symmetry force setting. Yeah, are there any questions about that? Is all of that clear? Okay, so now let's add symmetry to this picture. Now, all of this, of course, is more generally works for dimensions other than 2, but I'm just going to talk about dimension 2 for simplicity's sake. So, because that's what I'm going to present a theorem on. So, okay, let S be a subgroup of the planar Euclidean isometries. And I'm going to let KNS be the complete gain graph on n vertices. And what I mean by this is that Kn has order of S arcs from I to J, each labeled by a distinct element. Of S. And also we're going to have cardinality of S minus 1 loops at each vertex for each non-identity. And I'll show it. So for example, so K2 of Z2 is going to be this gain graph. So this is vertex 1, this is vertex 2. I'm going to have 2 arcs going from 1 to 2, and 1 arc or 1 loop at each vertex. I'm going to label the arcs between vertices by the distinct elements of the group, and then the loops by the non-identity elements of the group. Okay. And then one other definition I need. For each arc, E of KNS, define D of E to be the following polynomial. It's going to be the norm, or norm squared of x, and I'm going to define this notation in a second. X at S of the source of E, Y of the source of E, minus phi of E applied to X target of E, Y target of E. Oops, sorry. That should be phi of E squared, where phi of E is the gain of E. SO of E is the source of E. And then TA of E is the target of E. Okay, and then since phi of E is the gain of E, E is an edge in a gain graph with gain group S, and S is a group of planar Euclidean isometries. You can think of phi of E as just a 2x2 matrix. So this, hopefully this makes sense. Yeah, are there questions about that? Does DE make sense? Okay. Okay, so, and then finally, given this, for a gain graph, G, I'm going to define D to the G to be the polynomial map from R to the 2n to R to the arc set of G. To be the polynomial function where the component corresponding to E is D sub E. Okay, so I have this polynomial D of E that I can associate to any edge of any gain graph with gain group S. I'll fix a gain graph G, and then I get this polynomial map just by having, for every edge, I just take that function. And so you should think about this as analogous to the map that you would apply to a graph like in the rigidity setting, right? Where every edge corresponds to a pairwise distance between 2 points. Now it's basically the same, except every edge corresponds to the pairwise distance between 1 point, the source of your arc, and then another point, which is obtained by applying the gain label of that arc to the target of it. Okay, and so the point of introducing all this is to remind you of this theorem of Schulze and Whiteley, which is that G is generically symmetry forced rigid if and only if the rank of the Jacobian of J, the rank of the Jacobian of D to the G is equal to the rank of the Jacobian of D Kn of S. Okay. Right, and this is you get exactly the familiar situation in the non-symmetric setting when you just take your group to be the trivial group. This just says that a graph is rigid if and only if the rank of the Jacobian of this distance map is the same as the rank of the distance map for the complete graph. Okay, so with this in mind, I'll now rephrase the initial motivating question as follows. For a fixed group S of planar Euclidean isometries, characterize the algebraic matroid of D Kn of S, or equivalently, characterize G such that the rank of the Jacobian of D to the G is equal to the rank of the Jacobian of D to the Kn of S. Oops. All right. So hopefully the question is clear. I'll get into now how we'll be able to solve this for the case that S is a group of rotations. And in order to do that, I need the following definition, which I actually introduced the last time I gave a lecture in this course, to give you the Lovash and Yamini theorem. So let F from 2 to the E to Z be an increasing submodular function In other words, if A is a subset of B, f of A is less than or equal to f of B. That's the increasing part. And 2, f of A union B plus f of A intersect B is less than or equal to f of A plus f of B. Then define M of F to be the matroid where I is independent if and only if for all subsets I prime of I prime is empty or the cardinality of I prime is less than or equal to f of I. Okay, and yes, this does define a matroid. This is a theorem of Edmunds. Yeah, and again, I mentioned this in the previous lecture I gave, so this hopefully isn't a surprise. And the main example, which I presented last time I talked in this course, is that if R function on the edge set of the complete graph, just ordinary graph, not gain graphs, to C is the rank function of Kn's graphic matroid, then the 2D rigidity matroid is M of 2R minus 1. And this is essentially that Lovász-Jiminy result. Okay, and I'm reminding you of this because a very similar thing is going to be true for the symmetry 4 setting when it is a rotation group. Okay. So, and so yeah, the punchline of this next whiteboard is basically going to be an analogous thing holds for symmetry 4 rigidity when S is a rotation group. In order to do that, I need to define you now the analog of the graphic matroid, but for gain graphs. And this is something that is very important in rigidity theory for reasons that are way beyond the scope of this course. But here's the definition. Let S be any group the gain graphic matroid on Kn of S is the matroid on ground set the arcs of Kn of S. Wherein a graph arcs are said to be independent. Oops. If the graph has at most one cycle which is not balanced. Yeah, and I guess Tony went over what it means for a cycle and a gain graph to be balanced. And just to give you an example, or two examples rather, or an example and a non-example. Let's say S is Z2. I'll give these gain labels, say 0, 1, 1, 1. It just doesn't really matter which way I orient this when Z2 is your group. But let's say I orient this in a cycle. Okay, so on the left here, this graph has exactly one cycle. And as you can see, it's not balanced because as I sort of walk around, as I do a closed loop, the gain I'm going to get is 0 times 1 times 1 times 1, which is 1, or I guess plus. However, this graph on the left, this is not independent. So it also has one cycle, but that one cycle is balanced, right? Because if I do that same closed walk, the gain I'm going to get is 1 plus 1 plus 1 plus 1, which is 0. So this is independent. This is dependent. Okay. And now finally, I can state this theorem. And this was proven independently in one paper by Malestein and Thuran, and then in a separate paper concurrently by Jordan, Kazinitsky, ITZ, and Tanigawa. And it says that if S is a rotation subgroup of Euclidean isometries, then the matroid of D to the complete graph, the complete gain graph for S is equal to M of 2R minus 1, where R is the rank function of the gain graphic matroid of Kn of S. All right, so are there any questions about that theorem?
Is this for D equals 2 or any D?
Yes, D equals 2. Yes, D equals 2. Thank you. Yeah, Euclidean planar. I'll put the word planar in there. All right, and then, in the remaining 25 minutes, I will sketch a proof. I guess I will prove this modulo one hard thing that I won't prove, but yeah. Okay. So yeah, how does a proof of this work? Well, okay, so I'm going to sketch for you a proof that is not what those original papers had done, but this actually appears in a recent paper of mine that sort of extends these techniques to prove something more general. But yeah, so here's the idea, and the hard part that I'm not going to prove for you is the following. Yeah, so this is a theorem of mine, and it says the following. let F and G be polynomial maps, be in the complex setting. Or sorry, let them be linear. Let F and G be linear functions. Let Rf and Rg be the rank functions of the algebraic matroids of F and G. Then the matroid of their product, which is a quadratic function, is just this matroid that you get from Rf plus Rg minus 1. So does the theorem statement make sense? Notation is a little overloaded here, right? So over here, this is this M on the left. This is the algebraic matroid of F and G. This matroid on the right. This function on the right is it's a function that's set valued, and this is the construction of Edmunds that takes a submodular function and constructs a matroid out of it. So this M notation is a little overloaded. I hope that isn't confusing. Okay, so this is the part I'm not going to prove. The proof, yeah, is in a recent paper of mine, and it uses tropical geometry, which is, of course, way outside of the scope of this particular course. But here's an example application of it. And consider the following change of variables. Let's say Ti is equal to Xi plus Xj over 2, and Si is equal to, Ti is equal to Xi plus Yi over 2, and Si is equal to Xi minus Yi over 2 square root of -1. I don't want to overload I. Okay, and this I'm going to use again later, actually, in the proof of the symmetry force characterization. But if we just do this in the regular rigidity setting, then Dij, which is equal to Xi minus Xj squared plus Yi minus Yj squared, just becomes Ti minus Tj times Si minus Sj. And then, since the algebraic matroid of Ti minus Tj is equal to the algebraic matroid of Si minus Sj, okay, where 1 less than or equal to I less than j less than or equal to n, 1 less than or equal to I less than or equal to j, sorry, strictly less than. Is the graphic matroid of Kn, M of Dij, 1 less than or equal to I less than j less than or equal to n, is equal to M of 2r minus 1, where r is the rank function of the graphic matroid. Okay, we saw this already. This is Lovász-Jomini. This is what I presented last time I spoke in this course. And it just follows from this theorem. Now, we're going to do the same thing for the same exact change of variables gives you like exactly the analogous theorem in the symmetry force case when you're dealing with a rotation group. So yeah, now let's continue on to the proof of the theorem of the symmetry force theorem. So again, the same change of variables are going to work. I just have to tell you like what the parameterization is that I'm changing variables of. So d of e is just going to be, just by definition, x source of e over y source of e. Okay, we're taking norms here, minus phi of e times x target of e, y target of e squared. Now, since we're dealing with rotation groups, phi of e has a very special form. Namely, this is just the following. It's just the matrix cosine of some angle, which I'll call theta of e, negative sine of theta of e, sine theta of e, cosine theta of e. Again, applied to x target of e, y target of e squared. Now, if I just write this out, bear with me, this is just kind of a mess. It's s source of e minus cosine phi of e x target of e plus sine phi of e y target of e squared plus y source of e minus sine phi of e x target of e plus cosine theta of e y target of e squared. Okay, so that's just matrix multiplication. Then applying the same change of variables from before. Gives that d of e is equal to t of the source of e minus okay, and here e is overloaded. Now I just mean the number e. E to the I theta of arc e times the target times t of the target of e. And then times s source of e minus e to the minus I theta of e y target of e. Not y, sorry, that should be s. So we can now apply the theorem where we set F is the polynomial map T source of E minus e to the I theta E T target of E as E ranges over all arcs of the complete gain graph. And then G is similarly, for the S part. But then this matroid, the algebraic matroid for F is equal to the algebraic matroid for G, is the gain graphic matroid. On Kn of S. And this is just sort of a basic matroid theory fact. See, say, Oxley. And then this gives that the matroid of dKn of S is equal to the matroid of twice the rank function of this gain graphic matroid minus 1. Yeah, where R is the rank function of the gain graphic matroid. On Kn of S. So yeah, that's all I wanted to say for today, and I'm happy to take questions if there are any.
So what happens for dihedral groups?
Yes, where does it break? So the problem, okay, so what worked out really nicely in this case, actually, what worked out really nicely in this case is that when you apply this change of variables, the T and the S's sort of like separate into these two like kind of disjoint linear forms, or these two linear forms where like the T's and S's never cross. But if now E were orientation reversing, the matrix you would get would look like this, except you would just have a positive sign there. And that messes everything up in the sense now that you would have like your T here and your S here sort of trade places. And so now sometimes, you have your T's and S's together, sometimes they are separate. And this is what messes things up for the dihedral case. You can't just cleanly separate your polynomial that you're taking the Jacobian of into like a product of two linear forms. It's now, I mean, but like something similar can be done. You can maybe think about having like this huge polynomial or this huge like thing of linear forms, and you're just multiplying together like certain pairs of them. But yeah, you don't get this clean product of just linear polynomials.